Picture a galactic symphony performed by an incalculable amount of stars, planets, and moons in exact harmony. An ageless orchestration, etched on the dark black fabric of the universe, playing with mathematical accuracy and poetic magnificence. But in this grand orchestra, there's one group that still confounds and challenges the astronomers, the exoplanets. These are not remote spheres revolving around distant stars, they are other worlds, each of them holding an unknown page of the universe's unscripted past. Concealed deep inside the body of our Milky Way galaxy, they could have answers to questions mankind has posed for thousands of years. Are we alone? Is Earth singular? Or is it merely one note of a grand galactic symphony? Of the innumerable bodies in our known universe, there's one exoplanet that has repeatedly piqued scientific interest, Proxima Centauri b, or Proxima B, which is its popular name. At just 4.24 light-years away, within the Alpha Centauri system, it is the nearest currently known exoplanet to our planet, a seductive neighbor whose enigmatic nature makes it one of the most intriguing travel destinations in our quest for extraterrestrial life. Some scientists have gone so far as to dub it Earth's twin, a big call, and one that generates as much skepticism as enthusiasm. Let us venture forth, through time, space, and imagination, to discover why Proxima B, and exoplanets such as it, are the new frontier for science and discovery. And at the center of that discovery stands the most technologically advanced space observatory ever constructed, the James Webb Space Telescope, JWST, our window into the cosmos. To begin with, imagine the scope of the challenge. In just our own Milky Way galaxy, we have astronomers estimating there are as many as 1 quadrillion exoplanets. That's a 1 followed by 15 zeros. To put that in perspective, if all of our exoplanets were the size of a grain of sand, we could not only fill up the Grand Canyon but form a new one, perhaps spanning an entire continent. And within this mind-boggling number, about 20% are thought to be Earth-like, with rocky terrain, temperate climates, and atmospheres that could, under the right conditions, support life. That equates to 200 trillion Earth-like worlds, many potentially accompanied by moons, each of which could harbor its own ecosystems. We're not just looking for another Earth, we're searching across a canvas vast enough to include entire civilizations. Enter the James Webb Space Telescope, the flagship of contemporary astronomy. A technological wonder decades in development, JWST launched in December 2021 and has rapidly rewritten the book on what's possible in observational science. Unlike its predecessor, the Hubble Space Telescope, which was so dependent on visible light, Webb exploits infrared wavelengths to look deeper into space, and further back in time, than ever before. Its enormous 6.5-meter gold-coated mirror gathers weak signals from ancient galaxies, frigid star nurseries, and most importantly, the exoplanet's atmospheres billions of kilometers away. Imagine Webb as a cosmic detective, not just looking at the stars, but questioning them. Its instruments are designed to dissect starlight into precise spectra, showing the chemical fingerprints of elements and molecules. It can assess whether a planet's sky has oxygen, carbon dioxide, methane, or water vapor. Organic compounds, the fundamental constituents of life, can even now be detected from millions of miles away. In other words, the telescope reads for us, decodes the universe, rather than merely observing it. And that brings us to Proxima B. Found in 2016 by the European Southern Observatory, Proxima B was found using a technique known as radial velocity detection, where it detects small wobbles in a star produced by the gravitational pull of an orbiting world. Proxima B startled astronomers immediately. It was a rocky world, roughly 1.3 times the size of Earth, and situated in the habitable zone, the area around a star where temperatures permit liquid water to flow. Cosmically, it was a slam dunk. If there ever was a candidate for extraterrestrial life, this was it. But Proxima B revolves around Proxima Centauri, a red dwarf star that's infamous for its flares and radiation storms. These celestial tantrums might strip a planet of its atmosphere, making it uninhabitable. But new simulations indicate that if Proxima B has a magnetic field, or an atmosphere thick enough, it might be able to shield itself, just like Earth. And this is where JWST comes into play. By studying the atmosphere, or absence thereof, of Proxima B, Webb would be able to decide if the planet is barren or full of life, a rocky uninhabitable world or a biological haven. More intriguing still, the rotation of Proxima B is likely tidally locked, such that one face perpetually gazes towards the star and the other side is forever in darkness. This results in extreme conditions, burning hot on one face, icy cold on the other. But in the twilight zone in between, where temperatures are moderate, life may still be able to gain a foothold. Consider the whole biosphere of the world being in a state of constant twilight, a strip of life hanging by the edge of night and day. Not only is the idea scientifically plausible, but it is richly poetic too. So how do we explore such a world without actually being there? The James Webb Telescope applies transit spectroscopy, measuring starlight as it passes through the atmosphere of a planet as it orbits. The light is changed by the gases it travels through, and the changes inform us what is there. For example, a dip at certain wavelengths would suggest water vapor, and other dips suggest methane, carbon dioxide, or ozone. Combined, these can not only indicate habitability, but possibly biosignatures, molecular signs of life. And then, late in 2024, something remarkable occurred. While conducting a routine scan of the Proxima Centauri system, scientists analyzing JWST data picked up on an unusual electromagnetic signal coming from Proxima B. It was narrowband, and that it covered very few frequencies, unlike the vast majority of natural sources. And it was repeating in some kind of structured rhythm, which surprised scientists. Although the word techno-signature was tentatively introduced, it could not be verified if it was the result of intelligent life or some enigmatic cosmic phenomenon. And then, just as suddenly as it came, the signal disappeared. It didn't recur. It wasn't seen again on follow-up. But its fleeting existence shocked the scientific community. We were no longer talking about Proxima B in terms of the possibility of life. We were now discussing possible intelligence. While the formal response was measured, nobody wanted a repeat of the wow. Signal debacle, indoors, agencies around the world allegedly intensified scanning of Proxima B. The enigma remained. Was it a test pulse from an ancient extraterrestrial probe? A rare but natural stellar phenomenon? Or perhaps a one-time data anomaly glitch? Since there was no repetition, science could not come to a conclusion. But fascination with Proxima B grew. It was the topic of scientific meetings, NASA press conferences, and even esoteric think tanks with scenarios for first contact. As we stood by for more proof, another radical notion was born, this time from Harvard's Department of Astronomy. Under the leadership of inspiring scientists, these researchers suggested a revolutionary solution. Rather than just looking for radio signals or infrared heat, why look for artificial light? That is, they simply posed this question: if there were an extraterrestrial civilization on Proxima B, could we see the glow of their cities at night? Employing algorithms capable of distinguishing between natural starlight and man-made light, JWST was retuned to start looking for such indications, not only on Proxima B but also on a number of other exoplanets of interest. The idea was drastic but logical. Just as cities on Earth radiate photons observable from orbit, so might extraterrestrial civilizations radiate observable luminescence, fluorescent, structured, and differentiable from natural planetary albedo. Imagine that. From more than 4 light-years away, we might someday see a small, ordered twinkle on Proxima B's dark side, a dot of light that shouts, "We are here." The implications of such a discovery would be staggering. For centuries, we've looked at the stars and wondered. Our myths, our religions, our philosophies, all touched by the question of other life. To finally detect even a whisper of it would redefine biology, history, and even our spiritual frameworks. It would unite nations, fuel exploration, and possibly change the trajectory of human civilization. And yet, there's a rather chastening irony. With all our era's vast data, space-based telescopes, and dreams of interstellar travel, we've never been more conscious of how much we don't know. Every answer raises more questions. Is life widespread in the universe, or are we a fluke? Does intelligence always destroy itself, or stretch out across the emptiness? Are we looking for reflections of our own curiosity in the stars, or for something other than that? Proxima B is still a book left open. A cliffhanger of space. Its ground can be sterile or full of microbial life. Its atmosphere can be clouded with storms or spacecraft. Its oceans, if there are any, can harbor alien fish or future submarines. For now, we just know this: something exists there. And we are observing. In the years to come, new missions such as LUVOIR and HABEX will complement JWST in searching for exoplanets with yet more sensitivity. Rumors of a future interstellar probe, maybe a version of the Breakthrough Starshot project, are already in the air, with a view to reaching Proxima B sometime in the decades to come. Until then, we will depend on light. On pixels. On the patient parsing of signals by a telescope drifting a million miles from home. We will keep dreaming, observing, hoping. Because somewhere in that great cosmic symphony, Proxima B might yet sing back.